Swayam Prabha. Digital India. Educated India.
In our previous lectures, you have noticed that we are gradually improving our design of the machine. So, the steps which we follow to design a machine or a mechanical system the first task which we accomplish is analyze the kinematics. Which tells us about the movements of various components and parts of the bodies in accomplishing the described task. Next, after the basic kinematics is taken care of, our next subject or topic is dynamics, and of course, statics also will be a part of it. In this step, what we find out the actual resultant total forces and moments acting on various members and components. That is, next we get the forces and moments. Once we get the forces and moments acting on the various components, and once the chosen material we have prescribed with are given their properties of allowable stresses and such things, we can find out the dimensions, or we come to the stage of component design. At this stage, it is possible for us to find out the dimensions, cross sections, these, that all kinds of actual dimensions which will be used in making the machine. However, apparently it may look that our task is over. We have got the dimensions of the components of the machine, which will satisfy the kinematics prescribed, that means the relative movements necessary to accomplish the task. However, we have seen that the task is not over. What we did next to make the system run in a nice manner without showing too much of vibration or instability, we balanced the inertia forces. That made the running of the system much smoother. That was necessary to provide a reasonable length of life for the machine we have designed. Next, we found that was not enough to have a smooth operation. It was also necessary to go through a stage which we call as power smoothing. How we did it, we have seen it in our previous two lectures, that we add artificial inertia in the form of flywheel that smooths out the fluctuation on the operating or running speed. Is the task over? That is the question now. That means, can we consider that now we have come to the final stage of our design, where the machine can be fabricated and expected to be yield the required result. In fact, the task is still not over, and in this module we will see what next needs to be done. Now, why the task is not over? Let us look, or let us examine the question. any mechanical system we design which runs, generally you will find that all these kinematics, dynamics, etc., what we have gone through, that to do that we had to assume some operational speed with which the system is running in the normal condition. And we design the whole system based on that. So therefore, as a result, what happens that if we plot or if we find out for any machine, engine or anything, we find out its efficiency of operation, we plot against the operational speed, we will get a curve like this, and where this is the range in which we should remain. Though ideally we should consider only one speed as the speed at which it must run, but in practice it never really happens. But at the same time, we cannot deviate the speed too much from that optimum speed at which we get maximum efficiency. So our primary objective is to remain very near the optimum operational speed. So where we need this, let us give examples. An engine. An engine, when we design, we are very concerned about its efficiency. Or the turbine, we are very concerned about the efficiency because it is consuming fuel and producing power. And it is known that such machines or engines must be run at the operational speed where it runs at highest possible efficiency. And therefore, it is necessary, irrespective of the situation or circumstances, the engine always runs at the design speed or very near the design speed. There are other cases of situations or other cases where such kinds of speed control is necessary. A few common examples will be, if we remember our old gramophone, where the input or the source of power is a spring, a twisted spring which stores lot of potential energy, and gradually it is released and the record rotates and the machine runs. Or we have seen toys where we give lot of twist to the spring and it is loaded, and then we leave it, and we expect the system to run at an approximately constant design speed. So for example, if it is playing a music, we don't want the frequency of the whole operation to change, and we expect that the drum where we have the spikes which really drives the reeds to produce the music, it must rotate at a constant speed. But the input torque, that is which is coming from the spring, is gradually reducing because spring is unwinding. So in such situation, how is it possible to maintain a constant speed? So even this spring loaded or mechanical clock, we provide the energy in the form of a loaded spring or twisted spring, but the arms of the clock, they rotate at a constant RPM, though the driving torque which is coming from the spring is gradually reducing. So therefore, this is another situation where we need to control the speed, though the input is varying. Now let us see how or what are the parameters on which the speed of a running engine, say let us take the example of an engine, will depend. In a schematic form, an engine or in general a mechanical system, let us say, and there is input power in the form of heat or whatever it may be in case of engine, and we get output power. say for example, the engine is generating current or pumping water or running a machine tool, whatever it may be. And this output power, it means what? Load torque multiplied by operational speed. Now, if the input power remains constant, say for example, we don't do anything, we don't manipulate, load we are indicating by its torque and we are plotting speed of running when input is constant. So it is obvious that output power also will remain constant, though the load is increasing. Since the input power is constant, approximately we can say that output power also will remain constant. What does that mean? It means that this product load torque into speed will remain constant, and obviously speed will fall. If an engine is running some machine, suddenly the load torque increases, the speed is obviously going to fall. Or say for example, say a pump, if the head increases or somehow we want to increase the capacity or whatever it may you may have, you will find that increase of load may cause the speed to change. And therefore, such a system or such an engine or such a situation is not acceptable. We want our engine to run at maximum efficiency, which can happen only when it runs at the design speed. Similarly, if the load remains constant, sometime it may happen. Say like gramophone record, etc. The load is nothing but a constant friction or something. So here you will find input slowly changes, and therefore the speed you will find will depend something like this. If input falls, speed will also fall. Because output is approximately equal to input and load is constant, so therefore if the input falls, it means output will also fall, and load being constant, the speed will also fall. So this is another kind of situation. Some examples I have already given you, but more commonly encountered situation is like this. Now, how to then maintain the speed? So it becomes obvious to us that if here the load torque increases and we want to maintain the same speed at which is equal or very near to the design speed, there is no other way but to manipulate the input. We have to increase the input power. That means schematically the situation will look like this. So this is our system, the engine, it could be other machine also, and our speed, information about the speed is picked up. Some signal say voltage, which is produced by some tachometer or tacho generator here. We take this and we compare it with some reference speed. And we find if there is an error, whether the speed is more than this or less than this. Depending on that, we manipulate the input. So if the speed we find has fallen, we increase the input till this speed matches our reference. If it is found to be more, then we cut down the input so that the speed decreases till it reaches the reference value. This basic concept or principle is called feedback control. And this is what is achieved in mechanical system with the help of governors. So, this will be our topic of discussion, governor and governor mechanism. Now, in modern engineering, this feedback control or control is a very important subject by itself. However, in mechanical systems, the very primitive concept of feedback control is achieved through the application of governors and governor mechanisms for the past few centuries. And in this these few lectures we will discuss some of the common techniques of governor design. The first use, just to give you the history of this, the first use of a governor mechanism, which is nothing but a feedback control device, was by James Watt in I think late 17th century. So, the basic scheme is like this. Let us explain the simplest feedback control device, first device by James Watt, how it works. Engine is somewhere there which is running, and what is the source of energy to any engine, thermal engine, is steam. So, steam is going through this pipe, there is a valve here and is being supplied to engine. The engine, when it is running with the help of some kind of a belt drive, another vertical shaft is being rotated, whose speed is related to the speed of the engine. Now, because of this rotation, what happens that this balls, due to centrifugal action, it tries to fly down. Suppose if the speed increases from the design speed, what happens? It will try to go up. So, this sleeve will be lifted up. If this sleeve is lifted up, then this lever will rotate. about this 16. If it rotates, then this link will be pulled in this direction. That means this will rotate in this direction. That means the valve will close, as you can see. So what will happen as the valve tends to close, this steam supply will be cut down. If the input is cut down, obviously engine speed will come down and match the design speed. Suppose if the speed is below the design speed, then what will happen? Then this will fall below. If it falls below, because centrifugal force will be less now, because the speed of rotation will be less than design, so then obviously it will rotate in this direction, pushing the rod in this direction and opening the valve, so that more steam or more input energy is available. So this type of governor and this governor mechanism also bears the name of James Watt, and we call it Watt governor. So this is the most primitive and the first application of feedback control for maintaining a speed using a governor principle. Let us now see, of course, lot of work has been done after that, and currently the governors are far more sophisticated. Before we discuss a few of those, it is much better to have a bird's eye view about the whole spectrum of governor mechanism. Let us see what are the various types of governors. So we will use a tree diagram to do the classification in a graphic fashion. First, we divide all types of speed governing mechanisms into two classes. One class, as we have discussed, that we control the input with the help of a governor mechanism. We call them energy control type governor, like this one, where you are controlling the input energy. Another class of governor mechanism, which we will discuss maybe in the next to next lecture, where we don't have such elaborate arrangement, it has to be in miniature form, or maybe the nature of the problem is such that there we have always more energy supplied. We maintain the speed by controlling the dissipation of the energy in a suitable way. These kinds of governing mechanisms are called energy dissipative systems. And obviously, as you can see, this is a very wasteful method of speed control by allowing the energy, excess energy to be lost in friction. Obviously, we cannot use for major equipment or engine. Only for small devices where energy involved itself is not very large and dissipating a part of that is not going to cost us too much. So it is only very for special cases with a small and miniature system. Now this energy control type governors can be further classified into two groups. One is called centrifugal governors. The one I have discussed, the Watt governor, is a centrifugal type of governor. Here what happens that as the speed of rotation of the governor shaft decides the location of this heavy sphere, and that location will tell the location of the sleeve, that will decide location of the valve opening. And obviously, therefore, you can see that they are controlled by velocity. Or speed. Another kind of governor called will discuss these types of governors also, where the sensing of the change is done not from the sensing the change in speed, but directly from the acceleration which is going to be present if the speed is changing. So therefore, here the control is through acceleration. Obviously, you can see, since it senses the acceleration, which is instantaneous representation of the change in speed, it will be more sensitive. Whereas here, you have to allow some time to change the speed itself, and then only you can sense that something is different and I must take action. So obviously, this will be more sensitive. Now here again, these types of governors are further classified depending on the control, that means their restoration mechanism. Here, what actually tells this governor to come back, or this ball to come down and to take the sleeve below if the speed reduces? It is mainly because that the deflecting force, centrifugal force, which is being balanced or which is being balanced by some restoration, is nothing but the gravity. So it is the gravity which brings down the system, or it restores the governor always to the lowest speed position or collapse position. There are cases where the governor systems have been designed where the restoration to come back to some design position all the time is through springs. So we classify them further into two groups. One is gravity control, and spring control. Obviously, you can see that gravity control, that means to generate enough force to operate the whole mechanism, etc., with the help of gravity, the mass of these rotating spheres will have to be quite substantial, and they are quite heavy and bulky. On the other hand, you can generate substantial amount of force of restoration using even small or very stiff but small springs. So such devices are definitely very compact compared to the typical gravity controlled governors. Now let us consider the centrifugal governors first, that means which are controlled by the speed of operation. Now let us consider some important characteristics Now, these are some basic points one needs to always remember before discussing or designing this kind of governor. Now, one point is that sleeve, this is the sleeve. Which actually controls the mechanism to operate the valve. The sleeve will be at the lowest position where engine develops maximum power. Next important thing is, if the load is suddenly removed, the sleeve should reach its top position. That means it should change to a high speed situation very quickly. It should not be sluggish. Next, for normal operating conditions, the sleeve should float between the two extreme positions at the top and bottom. Generally, it should float. Response to changing speed should be very fast, as I mentioned, and this governing mechanism should have enough capability to generate adequate force to operate the valve control mechanism. It may do everything, but if the force generated etc. are very small, that it cannot really overcome whatever frictional loss etc. in operating the whole valve control mechanism is there, it cannot take care of that, then obviously the whole purpose will be lost. Now let us look into the basic definitions and concepts. The first important point you have to keep in mind is controlling force. What is this controlling force? So this sphere which is rotating like this one. Now from the central axis of the governor, so it is at any particular instant at a distance r, which we call the radius of rotation. Now suppose let us consider this, so it is not rotating, so then the ball obviously will not remain at some higher position, it will always try to come below because of gravity. Now to keep at this particular radius r, what we can do? Just a static condition, not rotating. What we can do? We can pull this by a outward force, and in such a manner that it remains static or stable at this distance r. What does that mean? That means that the various restoration mechanisms, whether it is by spring or by gravity, whatever it may be, at this radius, it effectively is producing a force towards the inward direction. So this is nothing but this is the resultant effect of all other whether gravitation, pull, the tension in the link, etc., everything together. It generates, or it can be considered to be equivalent to a radially inward force, which is nothing but restoration force for this whole system, and we call it a control force. And to find it out, now to keep it at this position, we apply a force in the outward direction, and what is this force? If we use D'Alembert's principle, you will find that this is nothing but the centrifugal force. So in a rotating condition, this force can be there because of this D'Alembert principle. We can treat that rotating condition or non-inertial frame system into a equilibrium inertial system if we consider a centrifugal force. That means when the centrifugal force is equal to controlling force, this sphere is going to remain at this location. That is the equilibrium position. And therefore, this controlling force of a governor is a very important concept, and it dictates lots of characteristics like this. So it is needless to mention that this control force is going to depend on the radius or the distance from the central rotating axis of the governor. So you can easily feel that sometimes the force required to keep it at a position by a horizontal pull will be more and more. You may require little force here, but gradually you have to increase. So this control force is a function of radius. So you can say it can be something like this. In general, it will be a curve, something like this. So when it is now rotating at some speed, now this force which is generated, the centrifugal force, which is nothing but m omega square r, where m is the mass of the sphere. And if you plot this for a particular speed omega, will be a straight line. This is F and this is Fr, control force. Now, the equilibrium position is indicated by the situation or radius where both of them are equal. So, at a particular speed, depending on the control force characteristics, the governor will run at a particular radius. That means with the balls rotating with a particular radius from the central axis. If what happens if the speed increases, it is very obvious that if you go from this speed to another speed, say omega prime, so obviously your radius at which equilibrium will be achieved will be high. So, it will now operate at this speed, which is r prime, or if the speed reduces, then it will definitely come down. So, therefore, depending on the speed, a governor rotates at a particular configuration, and that is what this is, therefore, nothing but a sensor of speed. Depending on the speed, you get a particular location of the sleeve, and that means any change in speed can be also sensed by movement of the sleeve, and that can be then used. So, therefore, governor mechanism is nothing but a speed sensor, frankly speaking, and it is not generating a voltage or electric signal, it is simply generating a mechanical movement or a mechanical configuration, which is an indicator of this. Next important point we have to keep in mind is the stability of operation. What is stability? Stability, as it is defined in many other cases, here also stability is defined by the situation what happens if the system is displaced from its equilibrium situation. If we displace the configuration little bit from its equilibrium running condition, and if it comes back to the original equilibrium position, it means the governor is running in a stable fashion. On the other hand, if it flies away, that means if we displace little bit from the equilibrium position, and instead of going back to its equilibrium position, it goes out, so obviously that will be an unstable situation. Let us consider the cases when a governor runs in a stable manner and when it is unstable. So, what we will do, we will plot this diagram as we have seen earlier, that this is the say control speed, controlled force diagram, and say it is rotating at a particular speed omega, and this is the deflecting centrifugal force. And obviously, our equilibrium position is now. What will happen if, that means without changing the running speed, the governor is rotating at the same speed omega, but we artificially shift the location from here to here. We give a push to the governor or the ball in such a way that it goes to a higher value of radius. What will happen? Will it remain there? No. We can see that now the restoration, that is the control force, is more than the deflecting force, and the equilibrium is lost. And due to that, what will happen? It will come back. That means since restoration is more, the R will reduce, and so will again try to come back to this original equilibrium position. Similarly, if we displace it to this location, give a push to the ball so that it is pushed inside, inward, what will happen? We can see now the control force is less than the deflecting force. So, the spheres or the balls will try to go out by increasing the radius. That means it will go towards. That means it is always trying to come back to its original equilibrium position, which is for that particular speed. And therefore, this situation is a stable operation. On the other hand, so this is stable. Here, this is the control force diagram, and now for a particular speed omega, this is the deflecting force m omega square r, and obviously the equilibrium position is where the deflecting force and the so it is running in equilibrium. What will happen if we push it without changing the speed of rotation of the governor to this location? Now you can see that your deflecting force is now still more than the controlling force. So rather than trying to come back to this position, it will further go out. Similarly, if we give a push of this governor, push to the ball so that we try to operate here, what happens? Now the control force is more than the deflecting force, so it goes further away from the original equilibrium position, and obviously this kind of situation is unstable. And as you can perhaps guess by now, the mathematically we can describe the situation or define that for stable operation what is needed is satisfying this condition. So you can see that the slope of the control force curve should be more than the slope of the deflecting curve, that is m omega square. Then it is stable. So dFr dr should be more than, now this dFr, this is nothing but tangent of this, more than the angle tangent of angle this. That means, and this is how much? This is f and this is r. So simply it can be written as f. So tan of this angle should be more than tan of this angle, and mathematically that is the condition which needs to be satisfied for getting a stable operation. There is another quantity which we should now look into, which is called the sensitivity, which indicates that how sensitive a governor is to any change. It can be very insensitive, you have to provide lots of changes, then only it will respond, or it can be very sensitive that slightest disturbance or slightest change in this situation can be changed by the governor. So if a governor operates between So here you know that, as I mentioned, a governor operates between two speed limits, maximum and minimum. It operates in that range. And if these two maximum, the upper limit is omega 2 and lower limit is omega 1, and mean operating speed, which is generally the average of this, is omega mean, then sensitiveness can be defined by this one. You can see if the governor, the limiting speeds are very near each other, that means it can operate only between, say, 500 and 501 RPM, then obviously 501 will be omega 2 and 500 will be omega 1 corresponding to that. And you can see it is a very sensitive thing. On the other hand, the governor has enough play, that means it operates at, say, 100 RPM at the lowest position and 700 RPM at the highest position. So that means there is a huge speed gap between the limit or the upper and lowermost positions of the sleeve. Then its sensitivity is very less. Now this can be, of course, omega mean is omega 2 plus omega 1 by 2 approximately. So this can be also treated as sensitive. If you know the maximum limit, you can find out this. Next very important concept in governor mechanism is isochronism. If a governor is at equilibrium at only one particular speed, then the system is called isochronous. So therefore, when it can happen? When the limiting speeds omega 2 and omega 1, they are same. That means it cannot have any equilibrium except at one position speed, one particular speed. So the governor is called the isochronous. That means what it will look like is we have plotted R and this is the force. If the control curve called control force curve is something like this, AB, and therefore in such a situation this deflecting force, the centrifugal force, can be equal to that only at a particular speed when the two lines coincide. Or you can see the slope of the deflecting force curve is m omega square, slope of the control force curve is df dr. When they are equal and they merge like this, the system is called isochronous. And it is also obvious here that since omega 2 is equal to omega 1, the sensitiveness or sensitivity of this particular governor when it is operating as an isochronous governor will be infinite. The other term which we should be familiar with, other characteristic, is the capacity. I have already mentioned that a governor has to do some physical work also by operating the whole valve control mechanism, and so it is important to have enough capacity, work capability of the governor, and this is defined as this, which is nothing but the work done so if this is the control force curve between the minimum and maximum operating radii, and this is the control force, then how much work is done by the control force when it falls from top, the highest possible speed position, that is Rmax, Rmin, is nothing but the work done by this force, which is the area under this curve, and mathematically is this. That means this is the energy released by the governor ball when the speed falls from the topmost to the lowermost position. Suppose you are operating at the highest possible speed, that means at balls are at Rmax. Suddenly suppose the load goes. So what will happen? Or load increases, what will happen? The speed will fall. Moment it falls, the balls would like to come to R minimum. While doing that, it will release this much of energy, and this energy is available to us for operating the whole governor control or the valve control mechanism. So we find that there are certain important general characteristics about these governors which we should be clear about, and then I think we can discuss different types of governors, different types of control arrangements, and we will discuss that in the next. So we will take up the centrifugal governors first and gravity control centrifugal force governors. Next we will take up spring control.